Civil engineering is a profession of massive physical variables. Practitioners manage heavy materials, complex bridges, moving workers, and critical safety zones. Every one of these elements exists in a complex, three-dimensional physical environment. Yet, traditional education forces students to learn these massive physical realities using flat two-dimensional tools. Textbook formulas, schematic drawings, and static video lectures are excellent for delivering mathematical theory, but they strip away depth, scale, and physical context. In the physical world, placing an untrained student on an active construction site to learn by trial and error is far too expensive and far too dangerous. As a result, students graduate with vast theoretical knowledge but lack the practical spatial intuition and safety reflexes required on an actual job site. When most people hear virtual reality, they immediately picture consumer gaming. But in high-stake industries, simulation is a requirement. Commercial pilots must master emergency protocols in high-fidelity simulators long before they are permitted to fly a real aircraft. Virtual reality applies this exact logic to the built environment. It serves as the flight simulator for future site engineers. In this context, VR is a completely computer-generated workspace that replaces physical surroundings with a responsive digital environment. The shift is physiological. Instead of looking at a flat screen on a desk, students feel as if they are entirely inside the physical space. This transitions students from passive observers of mathematical theory into active decision makers operating within simulated realities. A two-dimensional drawing provides precise mathematical dimensions, but it fails to communicate how a space actually functions or feels to a human user. Consider a staircase or a ramp. On a standard floor plan, the layout might look mathematically perfect. This split screen illustrates the discrepancy. While the 2D plan on the left shows correct placement, experiencing that same space in virtual reality on the right immediately reveals a critical ergonomic failure, blocked headroom. This diagnostic capability extends beyond architecture into structural physics, where the most critical engineering concepts are entirely invisible to the naked eye. Engineers must calculate abstract forces, load transfer, stress, strain, bending moments, and column buckling. Virtual reality renders these mathematical concepts as observable, glowing physical phenomena. The 3D wireframe maps load flowing from the upper slab down the supporting beam and column, dispersing into the soil. Manipulating variables reveal unbalanced forces like a beam bowing under excessive weight. We can even track microscopic cracks propagating through stressed concrete. Beyond static structures, civil engineering requires dynamic, time-sensitive material judgment on active sites. Engineers must evaluate raw materials under intense pressure. Wrong choices here waste millions of dollars and compromise structural integrity. The daily concrete pour is a prime example of a high-stake decision matrix. This decision tree evaluates instant site variables like slump value, weather, and formwork readiness. Electing to pour concrete despite failing condition registers as a critical error. The simulation then displays the delayed physical consequences of that bad decision, honeycombing and structural weakness. Testing failure limits like this on a real construction site is financially disastrous and highly dangerous. By operating as a consequence engine, virtual reality allows students to safely experience the catastrophic results of their own bad engineering choices. The modern construction site is an inherently dangerous environment requiring constant aggressive vigilance. Engineers must spot everyday hazards immediately. Unbalanced excavation pits, improperly supported scaffoldings, and workers missing personal protective equipment. Virtual reality accelerates the cognitive skill of observation by forcing students to identify these violations in real time, well before an accident actually occurs. This training scales up to extreme post-construction scenarios, specifically disaster management and evacuation planning. A building's structural integrity means very little if the layout traps its occupants. True safety requires rapid survival routes during an emergency. Engineers must anticipate dynamic disaster variables, dense smoke, blocked exits, power failures, and the unpredictable movements of a panicking crowd. Through simulation, engineers can test and optimize evacuation routes under these intense, rapidly deteriorating conditions. Virtual reality allows civil engineers to experience and mitigate fatal danger without ever being harmed by danger. There is a sharp contrast between interactive virtual reality and traditional video lectures. Video relies on a fixed camera angle chosen by an editor. Virtual reality demands that the student physically looks around the space and actively inspect the details. This comparison matrix highlights the difference. Video encourages passive observation. Virtual reality requires active participation and physical navigation. In standard education models, a mistake is a theoretical mark on a written test. In virtual reality, a mistake results in an immediate, observable physical consequence. Video teaches by showing a scenario. Virtual reality teaches by forcing the student to physically navigate it. Immersive training delivers critical cognitive upgrades. It builds spatial thinking, sharpens cause and effect reasoning, and develops professional confidence under pressure. Virtual reality is a critical piece of cognitive infrastructure for high-stake professions. It ensures that future engineers have made their fatal mistakes and learned from them long before they pour their first yard of real concrete.